This Thursday.
Wait, what?
But it's going to be a take-home quiz.
Okay.
So you're just gonna give us.
And I think from now on, just to save time in class, we're going to do take-home quizzes. And just so, and I'll say this again on Thursday, you could use any resource at your disposal, Wolfram Alpha included, to do it. Okay, but I would ask you to wait to the end to like do the problem.
Yeah.
I trust you guys. Do the problem and then use whatever technology to check your answer at the end. And if you find, oh, that's wrong, don't just scratch out one or two things. Just do it again, okay? Like, that's part of this. I'm going to be nice and give you take-home quizzes where you could use anything, but I want to see a good write-up at the end. So if you realize, oh man, I really screwed this up, I should have done that, just do it all over again. I want to see. So there's the double-edged sword of the take-home quizzes. I'm going to be looking for perfection, okay? Like, I want this to be tight, all right? And yeah, so there we go, and I think we're going to do that for the rest of the year just to save time so we can get more lectures in. If you guys absolutely hate it, let me know. We could talk about it and figure something else out, but I think this will probably work pretty well. Your final will be in person. Yeah, we'll do an in-person final, and it'll be longer, like usual. So, okay, so extra credits due. I think that's it. Any questions before we begin? Okay, excellent. So, you see these 3 series that I have written up here. You should be able to immediately recognize them. You should have them memorized. Okay, so like if at any point in your life you see this, you should go, hey, that's sine. I know that. That is sine, right? Ditto, cosine. Okay, you should also be able to interchangeably, if you have some expression written somewhere like 2 cosine x plus 1, you should immediately be able to say that's the same thing as 2 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. You should be able to immediately make that switch in your mind. Yeah. Ditto, if you see something like this, you should go, oh, hey, that's cosine. Like this, again, for the rest of your lives, you should be able to do that at all times. Okay? Okay. So, now, on to the topic for today. Jeez. All right. Note, this is a function. Okay? So this tells us that whatever we put up here, if you want to know, like, say, how to compute that, all you got to do is take that and plug it in, because it's a function. And we'll get into this a little bit. This works for all real numbers. No matter what real number you plug in for x, if you do this, it works. We'll talk about, so there's some times where that's not necessarily the case, but we'll get into that a little bit later. So, okay, for instance, let's say that for whatever reason you need to find the Taylor series of this function. One thing you could do is say, okay, Taylor series, I know what to do, I need a bunch of derivatives. So you start taking derivatives. You take the first derivative, and you get the derivative of e to something is that thing times the derivative of that, and that's 2x. And you say, okay, I need the next derivative. And so, oh boy, product rule. Okay, so here we go. Derivative of x is 1, and now add that to, I have x, and then I get e to take the derivative of the inside, and now the 2, I guess that's going to be a 2x squared. I could make that look a little bit better if I pull out a e to the x squared, and I'll have a 2 and a 4x squared. Okay? Now, I need the third derivative. Oh no. Product rule again. And you can see this is starting to get really, really, really ugly. Right? Yes. And you can imagine just how ugly it would get if you did the extra credit problem, right, where your f was 1 over 1 plus x to x squared. Oh boy. second derivative is ugly, third derivative is even uglier, and it never gets better, right? And then good luck trying to find a pattern, right? And let's say we're trying to find the Taylor series at 0. Okay, well, f of 0 is 1. Okay, f prime at 0 is 0. F double prime at 0, I guess that works out to 2. Okay, third derivative, again, right, you may or may not see a pattern emerge right away. But, like I said, this thing is a function. And so, it's the case that whatever I plug, whatever goes in up here is the same thing as this. And so all you have to do is this. It's yes, it is this easy. It is that easy. That's all you have to do. And if I'm asking you, hey, find the Taylor series of this.
So 1 over 1 plus x squared.
Yeah, let's go ahead and multiply them out so that it's actually in the form of a Taylor series, right? So it would be 1 plus x squared plus what?
X to the 4th.
X to the 4th
over 2.
Plus
X to the 6th.
6th over 3. And we could probably find, let's see, it's always 2 times whatever the top is. So when this is n, then it should be x to the 2n?
2n. X. Yeah.
Yeah. And I mean, you could have said, well, you know, this is the same. We know that e to the x, e to the whatever, is just whatever to the n over n factorial. And so if it's x squared, you plug in your x squared, and this is a sum from 1 to infinity, as n goes from 0 to infinity. And so that's the same thing, x to the 2 and then raised to the n is the same thing as x 2 times n. Right? So x to the 2 n, hey, look at that, that's nice. Right? Oh, I don't think I wrote it explicitly on the homework to do both ways. I would like, just so you, I would like to see it in both expanded and in summation. If it's possible, it should be possible.
Yeah, I think that's all.
Yeah, cool, okay. That's the same for this homework that you have tonight. Okay? Now, here's something. I was going to do this the last time, and I decided not to. But check this out. Okay, so, this is also true for any value you plug in here. So, I wish this black one was easier to erase. Okay. So, let's just think about the number e itself. The number e. We spent the summer doing a project on this, right? E itself is just e to the first power, right? Right. That's true for any number. X to the 1 is just whatever that number is, right? So if I plug in a 1, that's the same thing as this. Yeah? Yeah. Right? It should be. I mean, if everything I've been saying is true, it is. Then e itself should just be the number 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on. 1 over n factorial and so on. Now, I mean, if you chop it off anywhere, you have some kind of approximation of e. But you'd have to go on forever and ever to actually get the number. Right? Yeah. Everybody with me on that? Check this out, because this is cool. You remember when we were proving the existence of Euler's number?
Yes.
We had this. Our job was to show that this was less than some number. We needed to find some bound. Because remember, there were two parts. One, we needed to show that this increases, right?
Yeah.
That it's increasing. And if we could show that it's increasing and bounded, then we get the fact that there's a limit, right? And then we call the limit e. And as we were doing this, right, we said, okay, how are we going to do this? Well, we are going to use the binomial theorem to say, okay, this is the same thing as in the sum as k goes from 0 up to n of n choose k times 1 to the whatever, I think we did it as 1 as n minus k, and then 1 over n to the k.
Yeah.
And we say, okay, that's the same thing as, and I'm going to go ahead and boil this down, that's the same thing as factorial k factorial n minus k factorial. That's the n choose k. And then we had times the 1 over n to the, that's the same thing as 1 over n to the k. Yeah? Then we did some magic. We said, well, hold on. That right there is less than, and then I made this point, or equal to. Remember how I made a point about that? I was like, now, along the way, you might say, this, what you're doing makes it strictly bigger than, but I said, yeah, but there's a problem, because in the limit, right, we weren't taking a limit at the time, but in the video, I said, you know, you're going to see me do this a lot, and that's a habit from analysis. Why do I do that? Well, because sometimes you're going to set something up, and you're going to take a limit, and in the limit, you might actually get equality. You know what I'm saying? So like, for instance, it's always n plus 1 over n is always less than n plus 2 over n. But if I take a limit of these two things, it's the same thing. Right? Because n plus 1 over n, this is the same thing as 1 over n. 1 over n. This is the same thing as 1 over n. 1 over n. You see what I'm doing here? Right? And so this is the same thing as the 1 jumps over, we get 1 plus 2 over n. This is just 1. This is the same thing as 1 plus 1 over n. This is just 1. And now if I take a limit, let n go to infinity, right? If I let n go to infinity, this goes to 0, and we get a 1. Take a limit as n goes to infinity, that goes to 0, this is just 1. And so, in the limit, you need to have that equal sign right there. Because in the limit, it might, yes, while this is always bigger than that, it turns out that when you take a limit, they turn out to be equal because they're going to the same place. Right? Does that make sense? That's what I was saying right here, is like, I'm in such a habit of doing stuff from analysis that even though the step I'm about to take, where this thing here that I'm about to write is, yes, technically strictly bigger, in the limit it might not be. And here we go. So what did we do? We said, well, you know what? We did the cancellation, right? Well, let's just do the cancellation. We said, okay, we cancel the top and the bottom. Right, so this is n times n minus 1 all the way down to 3 times 2 times 1, right? That's the n factorial, you have your k right there. And then you have your n minus k minus 1 all the way down to 3 times 2 times 1. And you cancel all of these guys. And what you're left with up there was n times n minus 1 all the way down to n minus k, but then plus 1. Down here you had k factorial. Here, that's what you canceled, right? That's the bit that you canceled with the top. And now you have an n to the k. And then we noticed there's exactly k of these terms right here, right? So like 5 times 4 times 3 is a total of 3 things, right? And so if your 5 minus 2 were down here, 5 minus 3 were down here, right? There's your 5 factorial on the top. However many of those you knock off, that's the number of things you have left, right? If this isn't coming to you right away, go back and watch the video. But like, this really isn't the point of what we're doing today. We just noticed that the total number of things here, there are k things. And technically what I'm about to do is say, well, if I make each one of those bigger, if I make every single one of those bigger, so I make n minus 1, if I replace that with an n, and then the n minus 2, if I replace that with an n, it's bigger. All the way down to here, replace the n minus k plus 1 with an n, it is going to be strictly bigger, right? So that I have n to the k of them on the top, k factorial, n to the k right there. It is strictly bigger, but I said, I'm sorry, I have to do this. Because in the limit, if you're going to take a limit, they might turn out to be equal. But we could rewrite this as this right here. K goes from 0 up to n of, now it's just 1 over k factorial. What's 1 over k factorial? Well, 0, that's 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, all the way up to n factorial. That guy right there. Isn't that cool? We got 1 plus 1 over n raised to the n is less than or equal to 1 plus 1 plus 1 half. So now if you take a limit, they are equal. I just think that's cool. There's nothing really to take home from that. It's just, that's cool. So like when I was first doing this, because like I said, the whole reason that we did this, that I wanted to do this, was to prove definitively that E does exist. And I never saw a proof of that when I was in college, right? So I just did it. And like one day, like well out of college, I was like, I wonder if I could prove that. And that's how I came up how to do it, right? And the thing is, I knew that this sequence was E. And so as I'm doing this popped out. I was like, oh, hey, I'm on the right track here. Because I know that this is, if you continue it on, right? If you take the limit and the limit, then this is, the limit is the actual n factorial plus go on and on forever. That's what E is. That's just plain old E. And therefore, that limit is that. It's just kind of cool, man. Anyway. So, one more thing I want to say before we get into what the homework's going to be. So that's just kind of cool. I think that's neat how that pops out of there. Now, another thing, if you were doing it like this, remember, like we did this with a calculator where like we plug in a 10,000 and raise that to the 10,000, and it's still not a very good approximation at all. It's really bad. It's like, it's like 2.72, or not, it's like way off. It's like 2.76. And it's not until you get to like a couple million, you put in like a billion or something, and then you start to get 183. It's off right here, right? It converges very, very slowly. This guy, on the other hand, this sequence, if you go, the first, I guess if you call this 0, and then here you have 1. After 1 step, you have 2. Then after 2 steps here, you have 2 plus 2.5. Now you do your next step after 3 steps. It turns out this converges very quickly. And if you think about it, right, factorial blows up really fast. Right? Yeah. So, like for instance, 1 over 5 factorial, that's the same thing as 1 over 120. 1 over 6 factorial, I think, is 1 over 720. 1 over 10 factorial is like 325. It's on the order of 325,000. So it doesn't take very long of doing this until what you're getting here is tiny little decimal place. Right? So you're not adding much to that. In other words, another way of saying that is that this converges quickly. And now finally, to wrap up yet another thing from Algebra 2, is when you plug in something into your calculator, when you do this in your calculator, and you say like 7.8, you want to know because you're trying to compute what is e raised to the 7.8. What your calculator does is it computes this. It just goes, okay, what's 1 plus 7.8 plus 7.8 squared, 2 factorial plus, and it goes, and really, depending on the algorithm, it could probably know, okay, if you're at 7.8, then we need to go a certain number of them. Let's say it's 12. 7.8 to the 12, all the way up to 12. Because it knows that this number is dividing by 12 factorial. That's such a big number that that guy won't matter. Whatever 7.8 to the 12th power happens to be, once you divide it by something, and I could be off with this number, it might be 15 or something, but once you get out to here, you're dividing it by something that's so small that your calculator's not even keeping track of it anymore.
Yeah.
Right? Because your calculator only has like 9 decimal places that it's giving you. And so your calculator knows, hey, if this thing right here is smaller than the number of decimals I'm allowed to give you, I don't need to go any further. And this is how it computes it. Pretty cool, huh? Another thing, when you do something like this, you tell your calculator, I need a 1.3 and I need to raise it to the, I don't know, 2.07th power. I'm not sure, your calculator is probably, there are other algorithms and stuff like that, but if I were programming a calculator, the easiest, most straightforward way of doing this would be to say, well, this is the same thing as e to the log of 1.3 raised to the 2.07. Yeah. 2.07 log 1.3, e to that stuff. Your calculator computes what that is. We're going to call it c. And now I'm just going to say just take e times 2.07c, which is 1 plus 2.07c plus 2.07c squared over 2, and you keep going until you're at like over 10, and boom, that's how it does it. Pretty cool. Okay, so that's all I wanted to say about that stuff. Now let's get into actually using this stuff. Any questions on that? Oh, why not? Okay, so we never talked about how you might do this, but if A is, say, a matrix, there is a way of multiplying matrices together. We haven't talked about it. But if you have a square matrix times a square matrix of the same size, 3, 4, say 5, 6, there is a way of multiplying A times B and getting a new matrix which is the same size. And it'll have some numbers here.
Didn't you say it's not the same as if you multiply b times a?
That's correct. A times B is not the same thing as B times A. That is correct. But what you get is another matrix of the same size. So, there is a way of taking E and raising it to the power of a matrix. And all you do, turns out that that 1 is the identity matrix. Don't worry about it. Then you don't need to know anything about this. But this is just A times itself. Because you could take a matrix and multiply it by itself. It's just A squared. And so we could write this as A squared, or 2 factorial. Keep going, multiply it by itself again. That would be A cubed. Well, you just take A cubed, and so on and so forth. And that's how you could do that. I mentioned it was one day, Noel, when you weren't here, but we were talking about differential equations the day before. And Victor came in and asked,
I watched the video.
something, yeah, but this is before I started recording.
Oh.
And I mentioned how, because I said, you know how all of these second order differential equations, right, A, B, C, Like they all involve y being some kind of r e to the c t, right? All of those you could show have this form right here. I said it's funny how e pops into there. Turns out you can't, if you had same kind of thing, just a single function with its multiple derivatives, and you have to the nth power, the nth derivative, b times the n minus first derivative, all the way down to, let's just call it m, y first derivative, m, l, m, n, y to the 0th derivative. You have something like that. There's a way of changing this into a matrix. You could rewrite this, even this, you could rewrite any of them in terms of a matrix multiplication. And then the solution turns out to be whatever matrix you take this thing and you turn it into a matrix with n by n entries, and it turns out that the answer has this form right here. Some constant times e raises to that. And at the point I was like, can't really tell you how you take e and raise it to the power of a matrix. Now you know how. You take the matrix and just plug it into here. Although, again, we've never talked about matrix multiplication and stuff like that, but it's pretty cool. I highly suggest you take linear algebra. It's one of the coolest math classes you'll ever take. And it's really cool. Okay, so that's that. Now, so I had to go down that rabbit hole, but back to what we were talking about. This is a function. I could plug in anything into there, and this is valid. Okay. And so, in your homework, we found that this was true. Is this familiar?
Yeah.
Right? We had this. Actually, what we had was this. 1 minus x to the n plus 1 over 1 minus x equals this. We did this last year, I think. Oops. Right?
Yeah.
And we showed that that was true by just multiplying through, right? We had 1 minus x to the n plus 1 equals 1 minus x, 1 plus x squared, all the way up to x to the n. Yeah? First goes through, I'm sorry, this guy goes through and you get the 1 plus the x all the way up to the x to the n. This guy comes through and you have your minus x squared, all the way up to minus x to the n, finally minus x to the n plus 1. All these guys cancel. All you're left with is the 1 minus x to the n plus 1 right there. Everybody remember that? And so then when you divide by that, you get that. And that should work for every real number except for x equals 1, because it's going to blow up if x is equal to 1.
Yeah.
Every other real number, though, should be fine. And then, what conditions on x allow us to go on and on and on? What to the n plus 1? When you take the limit as n goes to infinity, it has to be what then 1? We want this thing to go to 0 as n gets really, really, really big.
Oh, it's supposed to be less than.
Yeah. Not just less than 1. Can it be negative 5?
Or less than.
Has to be
Less than
less
the
than
value of 1.
The absolute value of x has to be less than 1. In other words, the value has to be between negative 1 and 1, right? As long as x is in here somewhere, then it works, right? So like if x is a half in the limit, right, as n gets really, really big, half times a half times a half times a half goes down to 0. Same thing with negative a half. It might bounce back and forth. It goes, negative 1/2, positive 1/4, negative 1/8, positive 16, but it's coming down to 0 as n gets really big. And so we saw that this works, so as long as We said this works always, but we said if the absolute value of x is less than 1, then you could take a limit, and this gives us 1, because in the limit this thing goes to 0, and you get 1 minus x is the same thing as 1 plus x squared all the way up to x to the n, and you keep going. And that's what we found by doing it the hard way, right? By taking this function, taking its derivatives, finding a pattern, and figuring out the coefficients for the Taylor series at 0, right? This is something we didn't talk about. This only works there. Because let's just try it. Plug in a 5. What happens?
It's gonna
We'll have
31 plus
1 plus 5 plus 25 plus on and on to whatever 5 to the nth is, and then and on. It's gonna blow up.
Yeah.
Right. So.
But when you graphed it worked.
Did it? This is part of your homework tonight. You're gonna walk through a bunch of exercises with this. It doesn't work so hot outside of a certain range. If you just graph this function, it blows up here at 1, and negative, does it do, I think it comes up like this.
Yeah.
I think it does this.
Because negative.
Because negative makes it, yeah, negative x, that should, yeah. And so, this is 1, and when you're here, there's negative 1. When you're in here, then this approximation works really, really well, as you'll see. But when you go outside of it, that approximation no longer works. What I'm going to have you do is find the Taylor series at 2, and see what that tells you. And I'm going to have you find the Taylor series at negative 2. And you're going to investigate with Desmos. And I want you to come to some kind of conclusion about what's going on. But I can tell you right now, look at the original function. What's a very bad number to plug into there?
1.
You can't do it. 1 is not in the domain of this function. And so you have a problem depending on what side of that you're on. And all of the derivatives, by the way, they all have this form. Right? Every single one of the derivatives also has a problem when you try to plug in a 1. And so depending on what side of this guy you're on, your formula might change. Now, okay, so I've said that. It turns out, and I don't want to get into this in this class, but it turns out that every Taylor series has what's called a radius of convergence. Convergence meaning this series will converge. And as we've seen, if you plug in something into this one, say like 1/2, you'll get a legit number. Turns out to be 2. But like it converges to a value. If you're outside of this, like if you try to plug in a 2, you get 1 plus 2 plus 4 plus 8 plus, it doesn't converge. There's a radius. Why is it called a radius? Any ideas why it's called a radius of convergence?
Something to do with the circle. It's the unit circle.
Because if, instead of thinking about the real number line, you're thinking about that your x, like for instance, if we're thinking about this as a complex number, z, where z is some real plus I times some real, you would get the same thing here. And what it turns out to be is that given whatever number you've plugged in, like we did ours here at 0, the radius of convergence now means that any number that you plug in here with a radius of 1, that'll work in that formula. Just like in here. And so now you can see that, well, now if you take that complex case and you boil it down to just the real values, then yeah, whenever you're in here, from 1 to -1, it'll work. Turns out that if you plugged in some number up there, it would also work. That's why it's called a radius of convergence. Every Taylor series has a radius of convergence. And when we're talking about real numbers, it's just an interval on the real number line. Okay, so don't worry about that, because I just need to say that to be complete. Because we've run into this weird thing where it's like, you told me that the Taylor series works forever and always. Yeah. Thing is, we could now begin an entire, well, we could probably spend a whole year talking about this topic. Where does something converge? And if you go on to take analysis, you will spend 1 year talking about, given some series, how do we know what its radius of convergence is? You'll spend a whole year doing that, figuring out different tests for if you just have some general series, here's some infinite series. We want to know, does it converge or not? What kind of tests can we do to this thing? Here's one of them. You take a limit, blah, 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 and you see, is it bigger than, what is this limit equal to? And if that limit is equal to something else, blah, blah, blah. I don't even want to go into it, because you'll spend a year doing just tests to see if this thing converges or not. And that's something you could do right here, and there's one in particular where you could do on this, and you find that this thing converges no matter what value you put it in. In other words, its interval of convergence is all real numbers, or its radius of convergence is infinite. You could plug in any value, and this thing will converge. This guy, not so much. You can't plug in a 5 into him. He won't converge. Does that make sense?
So you can plug complex numbers into it?
You absolutely can. Yes, you can. And it'll work. This formula will work just so long as the complex number you choose is within the unit circle. As you're going to do, you're going to find what happens outside of here when you take 2. Maybe you get and if this were a class in analysis, in your homework I would say find the radius of convergence for this. But this isn't a class in analysis, so we don't care about that. It's just something you need to know happens to be true. Okay. E, sine, and cosine, they converge for all real numbers. I think I said that last time, but it's valid for all real numbers. You only really run into problems if your function or its derivatives blow up. So, just so you know. Okay? Oh, yeah, I wanted to leave that up there because this is the next thing we're doing. This is a function. And so, if I don't know, wanted to figure out the Taylor series for this guy, I could say, well, I know the Taylor series for this guy. And this is the same thing as this, isn't it?
Yeah. Oh,
right?
Yeah.
So I could just plug in a negative x into here. And I would get 1 plus negative x plus negative x squared plus all the way up to negative x to the n, right? And so on and so forth. And I could figure out the pattern and go, oh, okay, it's a minus plus. And so it does this. And then this. And then so on and so on. All the way up to negative 1 to the n? N times x to the n. Ah! That was way easier. Oh!
No. You do that for like...
Oh! So instead of taking a bunch of derivatives and having this thing get... Like in your extra credit, right? I gave you this. And I hope that what you did is you said, okay, alright, here we go, I'm going to do this. Okay, and then you did this and you went, oh no, and you get something like, I don't know, it's like this. I could be wrong about this.
After the second one.
And then you take your second derivative and go, oh no. and it gets really, really bad, and you're trying to find a pattern, or you could do this. You could say, well, hold up. If 1 plus x is this guy, then 1 plus x squared is the same thing as just doing this. Right? All the way up to negative 1 and x squared to the n. And so you could rewrite that
was
as
there a
1.
pattern? Because if it's
Yeah,
this simple, then why was there a way to
It didn't
simplify
look
that?
like there was a
I don't know. I'm not going to sit there and do that. It's ridiculous. You know, this is the same kind of thing. What we're doing now is the same kind of thing as when we learned how to take derivatives with the difference quotient, right? Where we spent a lot of time plugging in your function and then da-da-da-da-da-da-da. But then once we knew some basics, some atoms, like we got we know how to take the derivative of this. Therefore, we know how to take the derivative of this. Therefore, right? And then we figured out all those rules. This is kind of the same kind of thing. If you know an atomic, I'm just making this up, like, you know, an atom, it's a building block. This is like a building block of a series here. You could say, well, from that we could build up new series by using this thing. Yeah. Same like what I did with this. It's like, I don't need to go through. If I know that whatever goes up there, I just plug into here, well then I don't need to do all that work. And so that's how we could take care of this guy right here. Could have jumped straight to the chase, and here's another thing, right? Knowing that that's the case, don't necessarily need to do it in 2 steps as long as I'm very careful about how I do this. Because that minus x squared thing, right?
Yeah.
Right? You don't want to do minus x and then square it, because that's not what that is.
Yeah.
Right? So you got to be careful if you have minuses in your expressions and that you're doing it right, but this is the same thing as that.
Yeah.
And so I could say, aha, 1 plus minus x squared plus minus x squared squared plus minus x squared cubed, and so on. And you would work out that you get your minus and then your plus and your minus and so on. Okay, so be careful with that. Just like if I give you something like that, be careful. That's not minus x squared. That's not e to the minus x squared. It's not that. That is e to the minus x squared. So that is what needs to get plugged in. Just like this, right?
Yeah.
And so you get an alternating series. Okay, all right. Questions?
Yeah. I mean, like,
Yeah, I mean no. Yes, and by yes I mean no. All right. Okay. All right, so that's good. We got that. Okay. Let's find some more new series from old series. Who remembers what cosh is? It's
It's
the
like the
hyperbolic cosine. Who remembers what it is?
did we talk about
We did.
Briefly. We briefly talked about it, and I was like, you'll see why it's called the hyperbolic cosine. Like, what does this have to do with cosine? And what it is, it's this. It's e to the x plus e to the negative x all over 2. Looks nothing like cosine, does it? Like, what on earth could this possibly have to do with cosine? Let's see. What we could do, so okay, here's the question. Given f of x is the hyperbolic cosine, find the Taylor series for this guy at x equals 0. Okay, we could take a bunch of derivatives, and that's actually not bad. It's not hard with this one. It looks tricky, but it's really not that bad. But you do
It's
it,
just all
and
over
you'd
2,
find
so
a pattern, right? Yeah, the 2 would come out.
Yeah.
It's not bad, but it's even easier if you just go, well, I know what e to the x is. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And then I add that to, okay, negative x. The negative x would be minus, so all the odds would be minuses and all of the evens would be pluses, right? We did that already. So 1 minus x plus x squared over 2 minus x cubed over 3 plus x 4 and so on, all over 2. Now let's see. 1 plus 1 is 2. Negative x plus positive x is gone.
Oh.
That plus that
2
is 2 times x squared over 2 factorial.
Then it goes away.
Then it goes away. And then we have 2 times x to the 4. You see a pattern?
You can factor out a 2.
Which we will. So
And
now
twos cancel.
2 x to the 6th over 6. I
Oh,
think
then
that's
they
the
cancel.
pattern, right?
Yeah.
The 2's, we could just cancel all the 2's. And what we end up with is 1 plus x squared over 2 plus x to the 4th over 4 plus all the way up to x to the
So
2
it's
n.
cosine, but doesn't do the plus or minus.
It's a lot like cosine, isn't it? That's kind of cool. There's another reason why it's called the height, why it's related to cosine. We won't be able to see that until next time. We could do the same thing with sinh.
What is the graph of coach?
Yeah, graph it. You'll see. It looks like this.
That looks like
It's
a
just a
parabola.
parabola.
It looks, yeah, but it's not. It goes up much faster than a parabola. Okay, so this is cosh. Let's do sinh. Who remembers what sinh is? What do you think is the formula for sinh?
E to x
Minus.
Ah, that's it. That's it. That's the only difference right there.
That's a guess.
That's it. Oh man, I shouldn't have erased all that because we have our 1 plus x plus x squared over 2, x cubed over 3, minus each one of these. 1 minus, because it's a minus x, so now we have the alternating. Plus x squared over 2 minus x cubed over 3 factorial plus and so on all over 2.
So it's
1 minus 1 is gone. X minus negative x is 2 x's. Positive minus a positive is gone. X minus a negative is plus 2x cubed over 3 plus 2x to the 5th over 5 plus and so on all over 2 gives us x plus x cubed over 3. The only difference between the hyperbolic sign and sine is that sine has an alternating series, right? It goes positive, negative, positive, negative. This guy's just positive the whole way. Very similar. Pretty cool. So that's how you can get old series or new series from old series. And that's what you're gonna do. You're basically the first 6 or 7 problems is just find new series from old series. Which basically comes down to, if you know the series, plug in the thing. Very simple. Now, here's something I want to address real quick. You'll notice today I've said a bunch of times the Taylor series for, and I didn't bother to say the Taylor series at a point. And I made a big deal about that when we were talking about approximations. But I also said that, did you guys watch the video
yeah.
Of
When you
everything.
of,
graph
when, of
everything.
like how, was it cosine that I was doing?
Yeah, and how to graph down
Cosine.
distance.
And how the graph, like, it kept like going and going, and from that we're concluding that in the limit it's exactly the same thing,
Yeah.
right? Now, here's e to the x, right? And when we evaluate it right here, we see that the bigger that this thing goes to the Taylor approximation as n goes to infinity. The bigger we get, the more it goes to infinity, right? That's what we were saying, right? That the 1 plus the x squared over 2 x to the n over n factorial goes to actual e to the x whenever. Now this happens to be the Taylor series when we evaluate it here. So your first Taylor polynomial was this guy. Your second one looked like this, right? The third one looked like that, and so on and so forth. But as n tended to infinity, then we got the actual function.
Yeah.
What if we had evaluated it at 1? Which you did in your homework, right? I told you to find the Taylor series for f of x equals e to the x at x0 equals 1.
Yeah.
Anybody remember what you got for that?
It looked different.
It looked different.
It was like
First off, before we get the actual formula down, what do you think happens? The first one, the line looks like that.
yeah.
Then it kind of looks like a parabola that might do that. Then it gets a little bit harder. Do you believe that in the limit that this guy actually hugs him all the way?
Yes.
Right? Okay? And so what you're going to find is that f of x, what you should have found was that it was this. E over 1 x minus 1 plus e over 2 factorial x minus 1 squared plus e over 3 factorial x minus 1 to the third, and so on.
So it's the same thing, but you could factor out the e, and then you could.
So check this out.
Yeah.
My claim is that this thing is still e to the, even though it looks different, this does not look the same as 1 plus x squared over 2, and so on and so on. It doesn't look the same. We could sit there and multiply everybody out and hope that everybody cancels out. Or check this out, like you just said, factor out that e, and what do you got? 1 plus x minus 1 plus x minus 1 squared over 2 factorial plus x minus 1 cubed over 3 factorial plus. I said we could go back and forth with the Taylor series, right? Like if we wanted to find the Taylor series for this function, we could just plug this into the known Taylor series. Conversely, had I done that, that's what I would have obtained, right?
So that just equals e to the x.
So this is e raised to the x minus 1.
Which then is just the
Which is, indeed, look at that, e to the 1 times e to the x minus 1. That's the same thing as e to the 1 plus x minus 1. That is still just e to the x. Interesting.
Yeah.
Interesting. Now,
Could you do it anywhere?
with these, now the one that we were talking about a minute ago, the one that does not converge or converges in a special place, not necessarily. But with e, sine, and cosine, they should all be equivalent. In the limit, though. If you don't take the limit, if you only have it out to the nth one, well, then all bets are off. This only works. This only converges to that guy when you've taken n to go to infinity. Then you could say that those guys are the same. Here's another one that you did. So did that make sense?
Yes.
Like, it may not look like they're the same thing, but they are. In fact, and you could just say, we know that this is equal to that because they're both Taylor series that of the same function. They may have been evaluated at different points, but in the limit, they converge to each other. So for instance, from your homework, you had f of x equals cosine x, which we know is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. But I said evaluate it at x0 is equal to...
Pi over 2, I think.
think it's pi over 2. Where is it? Yep, pi over 2. And what you should have got...
The hardest one was one where you had to do pi over 4. Sorry.
Those are so bad. Those are terrible. And I'm sorry I had to do that to you, just so you could see how terrible it is. What you should have obtained was this. Oops. Yep.
Okay.
Yep. Should have had something like that.
Yeah.
Okay. Now, my claim is that this is equal to that. Now, unlike the last one with E, where you factor it out and you're like, oh yeah, all right, there you go. This would be harder to see. And we would have to, one way to do it would be to just multiply each one of these out. We'd have to find a general formula for that. It would involve n choose k, and it would be really ugly. But we would be able to get everything out. Or, check this out. Watch this. I'm going to factor out a negative. Factoring out a negative gives me this. Minus...
negative sign.
Yeah, you seeing it? And this is at the very beginning, what I was saying was be able to recognize these, and this is what I'm talking about. You should instantly look at this series and go, oh, I know this. This is what? What is this?
Sine of x.
Sine of x?
Minus pi over.
Ah, sine of
Okay.
this. If it were just x minus x cubed over that, x cubed, right? But it's not x, it's not just x. So this is negative sine of whatever goes in there.
X minus pi over
Is that the same thing as cosine?
2. Yeah, it's because you can plug in the 9.
Yeah, let's think about, so sine does this. Line over 2. Now, so this is sine x. And so subtracting off pi over 2 moves this graph what direction?
Right.
Right.
It moves it right. By how much?
Pi
Pi over.
Okay, so this thing that was here at minus pi over 2 then comes over by pi over 2.
Yeah.
So this trough is now here, and this one now comes over by pi over 2 up to pi. And so he does this.
Oh,
Let's
and if
do
you
that.
flip that.
And so that's just sine x minus pi over 2. And now if you make it negative,
Yeah.
it's going to flip everybody upside down, so you negative that guy and make him go this way. What function is that?
Cosine.
That's cosine. Oh, interesting. So my point is that though they may not look the same, right, as long as these things and the ones that we care about do converge everywhere, okay? Like it's not like the weird one where you end up dividing by 0 at 1, and so it doesn't work at 1, and so something different happens on either side of that. These guys converge everywhere. They're called entire functions. E to the x, sine x, cosine x are entire. Meaning that their Taylor series works on the entire complex number plane, but
What about log of x?
We did natural log.
Yeah, we
it's a
did.
weird one.
It is a weird one.
It's a weird one. That one does not work at 0.
Oh, because that involves 1 over x. And
Yeah, exactly. Because, yeah, log of x evaluated at 1. Okay, there's f. F prime is 1 over x. So you have a problem already, right? F second derivative should be negative 1 over x squared. Again, problem. There's one number where there's a problem.
You can't even plug a 0 into log of x, or any negative, so.
But what you could do is figure out a formula for it. And as long as you're not plugging in a 0, use the Taylor series for it. And it works. And indeed, that's how you define
Yeah, we did.
complex logarithm. You get your Taylor series, and it works out to be like, what was it? Like x minus 1 plus x minus 1 squared over 2 or something like that, right? Is that how, was that it? I'm not sure. I don't remember. It's something like this.
Yeah.
And you just say, you know what? As long as you're not plugging in a 1, you can plug in any complex number, even negative numbers.
It's a lot.
And that's how you get it.
I guess
That's
how it
you know, like I've said for years now. You can plug in negative numbers into it. You just can't plug in a 0 because that's the only problem there. Can you plug in a negative 1 into that?
Yeah.
Can you plug in a negative 2? Yeah, there's no problem there. So then this is valid as long as you're not trying to plug in some crazy stuff. And yeah,
Wait, we do negatives appear on the graph?
can you what?
Not.
But why don't they appear on the graph of log?
Because the output is a complex number. Turns out log of negative a is equal to the natural log of the absolute value of a plus some complex, some I times something. Yeah. Yeah, you get out a complex number. You get out an imaginary, it has an imaginary part when you do that. So if you try to plot it, it doesn't, like where do you plot
That's
that,
really
right?
complex things that way.
But over here, it's all reals. You get reals. You plug in a positive real, you get out a real. Down here, you plug in a negative real, you get out something that's in the complex plane. So
Desmos can do complex numbers
I
if you
think you can. You have to do something.
turn on a certain mode. Like
Yeah, there's a certain mode, and what it probably does is warps the complex plane. Like,
yeah, it makes it look weird.
yeah, it does, right? So what it does is it takes, like, grid lines. Like this. And then what it does is it says, okay, suppose you're here. Let's say this is 1. And so then any point here on this line, this point will have the form 1 plus I times t, as t goes from negative infinity to infinity. And then you plug that into your complex function, and you get out some kind of formula with t. Maybe it's like 1 plus 2i t plus minus t squared. And you say, okay, that's 1 minus t squared plus I times 2t. And now you could see, what does that do to this? Well, it might, as t, then now you have a parametric equation in x and y, right?
Yeah.
Something like that. And now you just have your points. As t goes from negative infinity up to infinity, now you have a parametric equation that does, it's probably going in the wrong direction, but it does something like this, right? And that's what it's doing. And so it's taking your grid lines and warping them like this. Pretty cool stuff.
Yeah.
And the one that I had in mind was f of z equals z squared. So you take your complex number, a plus ib, and you square it. And you get a squared plus 2abi minus b squared.
Yeah, because I
Yeah, which is a squared plus b squared plus I times 2ab. Now you can break that up and turn it into parametric equations, etc., etc.
Yeah.
Yeah, for any given point on the plane. Then you just do this. So are you talking about a horizontal line or a vertical line? If it's a vertical line, you just choose your point there, in that case 1, and then you let t go, and then you get this nifty parametric equation.
Yeah.
Here you do the same thing with either a or b. You choose your a or you choose your b, let the other one be t, and let that go from negative infinity to infinity, and you get your parametric equation, and you could regraph that, which was a grid line, into a thing. So, a bunch of stuff we didn't need to talk about today, but I kind of wanted to be complete. The big takeaway is, or the big skill to learn from all of this today is that you could figure out new Taylor series from old Taylor series.
Yeah.
And we are not going to split hairs about where does this converge. You're going to do one thing in your homework just to kind of investigate it. Like, something different happens over here. But if you're interested in that, go take a course on real analysis and you'll spend, it's terrible. It is mind-numbing. And it's cool, but it's just like, you spend so much time talking about where does this Taylor series converge? And that's great. So know that not every Taylor series converges everywhere, but the ones that we care about do. And you could treat them like regular old functions. Get new Taylor series from old Taylor series and all that good stuff. It's a really good skill to have.